Okay, I'm going to reply directly to Sean Carroll. I'm going to respond to each of his comments. Why does time exist? Why does time have a direction? How does complexity arise? And of course, does time exist is kind of implied. So the existence of time, and Sean showed us the standard physics picture. You have the block universe, time is an illusion. How do we reconcile the block universe picture with our intuitive understanding of time? The answer is it's the wrong picture. If you take time seriously, time passes as regards the contents of space-time and space-time itself, and instead of using the block universe, you must use the emergent block universe. So the standard physics picture, it's based on time-reversible Hamiltonian dynamics. There's a unique evolution from initial data to final data, and you can predict equally to the past and the future from the present-day data. There's no difference between the future and the past. And furthermore, there's nothing special about the present. It's just a convenient time to set data. Any old time will do, because it doesn't matter where you set the time. Now, the block universe, the past and future, therefore, are present, and the past, future, and present are all equally present. There's no intrinsic difference between them. So in the block universe, both the past and the future already exist and already uniquely determined. Nothing unexpected can happen, and the present has no significance. Okay, let's take time seriously. Things actually happen in time at the macro and the micro levels. There are reversible laws at the micro level, the Hamiltonian dynamics, but irreversible at the macro level, the second law of thermodynamics. And the fundamental feature of the macro world of physics and chemistry and biology is the flow of time. And Roger Penrose in his books writes about the breaking of a glass. You break a glass on the floor. In principle, the fragments could jump up again and reassemble them. In practice, it never happens. The processes of life also proceed in one way. In the real world, the past and future are not predictable from the present. In the real world, things actually happen. Now, Arthur Stanley Eddington, one of my heroes, wrote about it as follows. The second law of thermodynamics, entropy, randomness always increases. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There's nothing for it but to collapse in deepest humiliation. In classical physics, in the real world is not Hamiltonian. At large scales, dissipation takes place, entropy increases. Is it reversible at the micro scale but not at the macro scale? Is the apparent flow of time just a result of coarse graining and hence in some sense or other an illusion? No, complex systems really undergo time change at the macro scale. And what about at the micro scales? Well, things happen at the micro scales also. In quantum physics, the Schrödinger equation is unitary and time reversible, and you get psi 2 is a unitary transformation of psi 1, exactly the same as Newtonian mechanics, is all reversible. But that's not all that happens. Collapse of the wave function is where the indeterminateness of the future gives way to the definite state of the past. Things happen in quantum mechanics because we do experiments, we get unique results out. When we do a unique result, what was indeterminate becomes, at least for an instant, a determinate result. And that's how classical physics emerges. The outcome is unpredictable from past data, as Sean said, and that's where the real dynamic change takes place, is when you do the measurement. Quantum physics is not time reversible because measurements are a crucial part. And the point about this, physicists talk about the results of statistics of results of ensembles and so on. You can't get a statistics of result unless individual results take place. So you cannot talk about the statistics unless firstly the individual results, and that must involve this collapse of the wave function. The claim that it is time reversible, referring only to Hamiltonian dynamics, can only be made if you ignore making measurements, and therefore, as I said, you can't talk about the results of probabilities unless you have individual results, and so you can't ignore the measurement problem. If a measurement takes place at time t star, initially the wave function is a linear combination of eigenfunctions of the operator A that represents A. So for t less than the measurement time, the wave function is a sum of eigenstates. But immediately after, the wave function is an eigenfunction. And this is this is just a standard part of standard quantum mechanics for some specific value n. The data for t less than t star do not determine the index n. They just determine a probability for the choice of n. And I think of this, as many people do, as Roger Penrose, as due to the probabilistic time irreversible collapse of the wave function. The initial state does not uniquely determine the final state. It's not due to lack of data, it's due to the foundational nature of quantum interactions. You can predict the statistics of what's likely to happen, but not the unique actual physical outcome, which unfolds in an unpredictable way as time progresses. You only find out what the outcome is after it has happened, and that's the point about it. So you can't predict the future, you find out what happens as it happens. In more realistic cases, there's a projection into a subspace of the full Hilbert space. Measurement affects some features of the system but not others. The principle remains the same. Now, I know many people would like to invoke a many worlds Everett description, but it doesn't help in practice. In practice, the actually experienced universe is one in which you make the measurement n is unpredictable, as I've just said, and thinking there's a multiverse up there doesn't help us in our laboratory as we do our experiments. Furthermore, in general, the time is not predictable from the initial data. You don't know when collapse of the wave function will take place. You can't predict when a specific excited atom will emit a photon or when a radioactive particle will decay. You don't know the result, but you don't even know when it will happen. But most important, we also can't retrodict to the past at the quantum level, because once the wave function has collapsed to an eigenstate, we can't tell from its final state what it was before the measurement. So if you know the result 2, you cannot reconstruct state 1 because there isn't any information in 2 which enables you to go back to state 1. And so there is irreversibility in this micro collapse of the wave function. Knowledge of the later states does not suffice to determine the initial state. The set of quantities psi n are not determined by the single number an. This irreversibility is reflected in the non-unitary evolution of the density matrix in dissipative systems. When a system interacts with the environment, the evolution of a reduced density matrix is given by the Lint-Black-Master equation, which is written down there. There's a dissipator representing irreversible effects and the increase in entropy that results when you coarse-grain the environment and see its effect on the system. This affects not only the content of space-time, it affects space-time itself. Consider a massive object with 2 computers that control rocket engines that move it right or left. Let the computer determine the outcome of whether it moves left or right on the basis of measurements of decay products of excited atoms. Then the outcome is unpredictable in principle, and if the object is massive enough, it curves space-time. And then the future space-time structure is not determinable or predictable from current data. So what you have there, on the left, you have a particular time, and this massive object has got rockets going both ways, and decay takes place and tells it whether to go left or right. That's unpredictable. So at the time on the left, everything is determined up to the horizontal time t1. There's masses of possible options in the future. On the right, we've gone up to time t2. One of the options from t1 to t2 has been selected. You see there the paths not taken on the left, and at time t2 there's now a smaller set of paths as options going up to the right. That's the change from uncertainty to certainty. The present is where the indefinite future changes to the determined past. So the evolving block universe grows with time. The determined past is there and fixed. The indeterminate future is not yet there and still has to be. And this is what happened in inflation. If you knew what the state of the universe was at the beginning of inflation, you cannot predict what the result will be at the end of inflation, because quantum fluctuations came in and decided what had happened. So if you know the universe at the beginning of inflation, you cannot predict that this planet or this galaxy will exist. The present, as I say, is where the change takes place. It's crucially different from the past and the future. Indeed, it separates them. So the future does not exist in the same sense as the past or the present. The determinate region grows with time. Space-time is growing. And this is the evolving block universe. As time goes on, space-time increases. There's nothing up to the future. There's only possibilities. What is determined is the past. The nature of existence is different in the past, the present, and the future. Physically, this happens along time-like world lines rather than on space-like surfaces, as Stephen Savitt said yesterday. Global time is derivative, not fundamental. You start at the beginning of time, measure time along fundamental world lines since the start of the universe. You determine the present transition as time evolves along these fundamental world lines. Which world lines? The average motion of matter, the unique eigenlines of the stress tensor T, which are also the unique eigenlines of the Ricci tensor RAB. So change happens on preferred surfaces that need not be simultaneous or even space-like. This time of determination is globally determined, not locally. It's fixed by how it started at the beginning of the universe. It isn't Lorentz invariant, it isn't covariant, quite right. This is a classic example of a broken symmetry. There's no reason to believe it should be either the Lorentz invariant or covariant. That's the way broken symmetries work. So in the evolving block universe, the present is where this change takes place. In a lumpy universe, it goes all lumpy. Why does time have a direction? How can a difference emerge between the future and the past? The microphysics doesn't know the difference. How does time know which way to flow? And more important, or as important, why does it flow the same direction everywhere? It can't come from the microphysics, so Boltzmann's H theorem does not give you the answer, as Loschmidt pointed out, Rogers pointed out, and Sean has pointed out, because you can apply Boltzmann's H theorem to say that entropy will increase in the future, and it will. You can apply it to go to the past. It'll tell you entropy will increase to the past as well. That's Loschmidt's paradox. So it doesn't help. The H theorem, and it can't help because you can't get an arrow of time out of physics which is time reversible. The data isn't there to get the arrow of time out. The microphysics is time symmetric. The future and the past are equal. How does macrophysics know the direction? In the block universe, they're equal. Not so according to the second law of thermodynamics. So what happened? Well, why does have time a direction? At the macro scale, the answer was given by Sean. The past hypothesis, observable past, was in the low entropy state that underlies the increase to high entropy. But that doesn't give an answer to the micro scale. It doesn't tell us how the quantum physics knew which was the direction of time, unless we link state vector reduction to the expansion of the universe. Now, Rogers' proposal does link state vector reduction to the universe, distant parts, but I don't think many people go along with Roger on this. My view is you can get this time at the micro level from the evolving block universe. The past exists and is developing to the future, which doesn't exist. It is this asymmetry which could hopefully lead to the micro arrow of time. In the evolving block universe, the difference between the past and the future is that the future doesn't yet exist, but the past does. The arrow of time is then built into the very structure of space-time in a foundational way. It affects the arrow of time in wave function collapse and hence all physics. How does it affect microphysics? By setting the direction of collapse of the wave function in the way I've just said. You can only integrate to the past. You can't use advanced and retarded green functions because the future ain't there. Now, you will run into problems if these world lines intersect, but that is when a space-time singularity occurs. So you will run into problems. We've always known that singularities occur if these eigenlines intersect. So that intersection can't happen regularly, but if you think about it, what this prescription does is it prevents the existence of closed time-like lines, which is a benefit of this approach. Finally, how does complexity arise? At the astronomical scale, because ordered structures such as stars and galaxies are attractors in phase space. This is the paradox of entropy and gravity, which is an unsolved problem in classical gravity. Gravity naturally creates structures in apparent violation of the second law of thermodynamics, despite or because of its Hamiltonian dynamics, and hence creates habitats for life. Nobody has yet got a proper description of how entropy behaves when systems are gravitationally collapsing. The entropy is presumably increasing, but structures are forming, contrary to what every textbook says about the relation between entropy and structures. So the unsolved problem of gravitational entropy is here, which I've talked about a lot with Paul, and we are making progress towards a solution, but we haven't solved it. But let's get down to the interesting one, in a sense, or it relates to what we're talking about. How does complexity arise at the everyday life scale? To some degree, it comes by self-organization, but self-organization, in other words, bottom-up growth of complexity, is very limited. The key process is adaptive selection, and we've heard a lot about that already today. This requires randomness to create an ensemble from which a preferred set of states is chosen and the other discarded. Now, the first point I want to make, selection can be a once-off event. In biology, it's multiply repeated, but the concept of adaptive selection is once-off. In biology, it gains its power by repetition, but that's not necessary to the concept of adaptive selection. And this is the key diagram of my talk. It's a notional picture. The way meaningful information is created from a jumble of disordered objects. So the jumble of disordered objects are coming up to a screen with a gate in the screen. Everything you need to know is down there in the jumble, but it's hidden in the ensemble because there's a whole mass of noise there, of other stuff there, and you've got to select out what matters from this jumble. So we have a selective gate which only lets through the stuff we want, and it stops, it blocks off in some way the stuff we don't want. And adaptive selection functions that way. It allows local gains against the overall flow of entropy by selecting a subset of the states in the ensemble, letting them through and blocking off all the rest. Entropy is decreasing as order increases. The classic example is Maxwell's demon. The selection principle in that case is the speed of the molecules. Meaningful information is gained by discarding all the information receded that's not meaningful. In this case, all the molecules that are moving slower than the gate you discard, you let the ones going faster, and that creates the difference. It creates the ordered state above and the disordered state below. But this is a very, very gentle principle. It implies irreversibility. Again, if you look at the top state, you can't go back to the prior state. That's where the irreversibility comes from. You haven't got the information above to go back to the state below. You can't determine the initial state from the final state, so there's a decrease in entropy because of the selection process. Now, in quantum physics, this is the process underlying state vector preparation in quantum physics. This is a non-unitary process that goes against the general increase in entropy. It has to be based in the measurement process taking place repeatedly in order to decide what to keep. When you when you do the process of state vector preparation, it proceeds in exactly this way. But each time you select, you have to measure what it is in order to decide what to elect through the gate. So a measurement process is involved there. Time flows at the micro level in the process of state vector preparation in quantum physics. It also flows at the macro level by repeated adaptive selection, building up biological information, as we've been hearing today, through enormous numbers of adaptive selection processes. That's a non-unitary and hence not encompassed in the unitary evolution of any wave function of the universe, if such exists. And the point about this, you can't assume Hamiltonian evolution applies to the universe as a whole. In fact, there's very good evidence that it does not. I've got a paper coming out about this in the archive tomorrow. Adaptive selection happens in any detection process. For example, this room is flooded with radio waves coming through. A radio receiver is awash in radio signals at all wavelengths. It selects only those of the right wavelength that you've tuned to and rejects the rest. That's an example of adaptive selection. Hence, adaptive selection is at least part of what's going on in the quantum measurement process, state vector collapse, because any detection apparatus selects what variables to respond to and ignores the rest. When you put a detector of spin in a vertical state, it ignores the horizontal state. So there's an ensemble of stuff coming in, and the detector selects the vertical as opposed to the horizontal. So that selection is a core part of the measurement process. This process occurs whenever we select information to make sense out of what is happening. Now, in computers, famously, entropy is generated when memory banks are cleared. What people don't tell you when they say that is you don't clear all the memory banks, you keep some. How do you decide what information to keep and what information to delete? That is where the information, the order, is created when you do that deleting process in a computer. It happens when you delete your emails. You've got all those emails there, you delete the ones you don't want and you keep the ones you do want. That's adaptive selection, where you are creating order out of that pile of emails, a lot of which were trash, you didn't want them. You create order by deleting the ones you don't want and you keep the ones you do. It occurs when you sleep and transfer memories from short-term to long-term memory. Your unconscious is working away there, deciding this is the stuff which is worth keeping. I'll move it from short-term to long-term, and this stuff I'm going to discard because I do not need it. And that's essential that the brain can function because we are awash with information every day. We cannot keep all that information every day because our brain would clog up. You have to clear space for the tomorrow, and that's the way that the sleep thing works. So in a profound sense, the arrow of time occurs in the human mind not when you remember things, but when you don't remember them. It's all the stuff you do not remember, which means that the stuff which does go through is the stuff which is meaningful for you in the future. In vision, it occurs when you look at a scene and filter out the irrelevant stuff to see what is relevant, and so it underlies human visual process. All the time as we look around, we're getting a mass of stuff coming in, and our selection, our mind selects the stuff which is relevant and discards the rest. And the same happens in reading. It's what we do when we're reading. We skip words and we only read sufficient parts of what is there to understand it. We unconsciously skip the rest. And Carol, my wife, has been working on this and showing how this happens with other colleagues when you read. In all these cases, this is the core place where time comes to pass as meaning making takes place by this process of adaptive selection, and the arrow of time is established. I'm going to give you an example. If you've seen this before, don't say anything, but for the rest of you, I'm going to give you a selection effect. How quickly can you detect the difference between these two pictures? Anybody see the difference? It's difficult to see the missing engine because the eye focuses on the people, because our mind is adapted to search for meaning in the people. And so it's quite extraordinary this. When you show that to two people, people do not see that huge engine, which is a very big effect there, because your mind is tuned to select the stuff which is meaningful, which is the people, and you don't look for the engine. It occurs when we form theories from a variety of half-baked ideas. The most powerful tool in a theoretician's toolkit is not a supercomputer, it's a waste paper basket. Indeed, adaptive selection underlies all learning processes of hypothesis forming and testing. And of course it occurs in biology. It's the deletion of ineffective variants, whether they're genes, individual or species. That's the core of the passage of time in evolutionary biology. It's the stuff which has been deleted and leaves the meaningful stuff behind. That's the way the process of time comes. And this is also true in nanotechnology. It's the way one creates specific molecules in nanotechnology processes. So, two final comments. Adaptive selection is a form of top-down action in the hierarchy of complexity. I won't have time to talk about that. But the point is the selection criteria, any adaptive selection is based on selection in a context. We were actually hearing about that in biology. If you change the context, you get different results from the adaptive selection. And so, in fact, this is a top-down process from the environment to what happens to what you are adapting. Change the context and there will be different outcomes. So it's an example of top-down action in my terms. Obviously, one needs an evolving block universe to express the way irreversible local entropy decreasing changes take place as adaptive selection takes place. You have to have a picture like the evolving block universe in order to represent adequately, to model in a space-time way what we've been talking about. And so we mustn't let our models of the physical world control the way we think. Our models may or may not be adequate. The block universe is not adequate for looking at biology and reality. The evolving block universe is. A block universe is an inadequate space-time model for what is going on when irreversible processes take place, and they do indeed take place. There is indeed a passage of time. The past is fixed and cannot be changed. The moving finger writes, and having writ moves on. Nor all your piety nor wit shall lure it back to cancel half a line, nor all your tears wash out a word of it. The future is not determined till it happens. That's guaranteed to us by quantum mechanics. It's what we experience in the macro world. And I'm going to give you a final example of how selection takes place in what you see in reading. So now, if you've seen this before, please don't answer, but if you have, I want you to read the following statement once, and as you are doing so, count the number of times the letter F appears. Anybody, when you have an answer, if you'd like to shout it out, read that and tell me how many times the letter F appears. 4. 5. 6. 7. The answer is 8. You don't see those letters. This is the simplest algorithmic task you can set yourself. You don't even see those letters, because we select what we read, and when we read that, we don't read those ofs. We put them in by our minds. We don't actually read them. And I've just given you a demonstration of adaptive selection taking place. It's the simplest algorithmic.
Obviously picking out the important things.
Yeah, you pick out what is important for you. You don't read the rest. That's adaptive selection in the way that we read, and that underlies the reading process for any advanced readers. Thank you.